Like I said, we're gonna get right into it because we got a short class today. So on this page here, we're integrating the natural exponential. So we're talking about e to the x. We're gonna do integrals of e and natural log today. So we're basically just reversing what we did last class. So just as a reminder, you don't need to write this part down in black because you have this written down already. The derivative of e to the x is e to the x. The derivative of e to some function f of x would be you keep the exponent the same and you multiply by the derivative of that exponent. So when we're integrating, we just go in reverse. If we're integrating e to the x, it's just e to the x plus c. We leave the exponent the same. And we can also reverse the chain rule. So if we see e to the something, and we also see the derivative multiplied, we can integrate that. Now we're going to use u substitution with this usually. And so just as a reminder, this doesn't need to actually be the derivative that we have there. It just needs to be a multiple of the derivative. And that's like our whole thing with u substitution is like we need to multiply u or divide, or sorry, multiply du or divide du to make it match what we have so that we substitute correctly. I'll say integrating things with e to the x are usually a lot easier than integrating things with natural log. It's always really obvious that we are integrating something with e to the x because like you're gonna have an e in the problem, always, 100%. Natural logs, because we don't have the natural log in the actual derivative, they look different and they get confused with other things. So we'll talk about that in a little bit. But let's take a look at some examples here. So if I'm integrating e to the 5x, I could use u substitution with this. This is a simpler one here. I know that my function is basically going to look like e to the 5x plus c, because I know that the exponent is going to be the same. We're not changing the exponent. What would I need to have out front to make this work? Would it be 5? It would be 1/5. So if we think about taking the derivative of e to the 5x, this would be e to the 5x times 5. That would be the derivative. So since there's no 5 out front right there, it must cancel out with that 1/5. So this is one kind of similar to like integrating cosine of 2x. You can use u substitution with it. You do really want to be able to do that in your head. The best way to check is always what?
Taking the derivative.
Yes. I do encourage you guys to actually do that. It's very clear on some tests and quizzes that some students are not doing that to check their answer because the answer is like so ridiculous and impossible. There's no way that could be the integral. If you just took the derivative, take 2 seconds to take the derivative, you would see that it can't possibly be the right answer. So please actually do this. Taking derivatives is way faster than taking integrals. So it really helps, I promise. Okay, so let's say we're looking at this one here. This one is slightly more complicated, so maybe we can do it in our head. Great. Or maybe it's just weird looking, and so let's go ahead and use u substitution. U substitution is going to work the same way. When we do u substitution, we want to make u the inside function. So we always have like an outside function, an inside function, and the derivative of the inside. Those are our layers in u substitution. This is the one that we want to make u. And this is what's going to become du. And I guess the outside function is what we actually integrate. So when we're looking at e to the 1 minus x times 4, what is the outside function? E. Yep. E to the blank. What is the inside function? One minus x. Yep. What is the part of this that is a multiple of the derivative of the inside? What's left? 4. Okay, so now we have all of our parts accounted for. Now, is 4 actually the derivative of the inside? No, but this is why we do u substitution. So we make u 1 minus x. We take the derivative, which is what? Yep, -1 or negative dx. Okay, we've got to get that to match 4, since that's what we have. So what would we multiply by? -4. And so now we can replace everything in our function. So we have -4 on the outside. E to the e to the u du. Yeah.
Can you take the 4 out front before
Yeah.
you...
Yep. So when we actually go to integrate, when we integrate e to the u, it's just e to the u plus c. Yep. So we have -4 e to the u plus c, which is -4 e to the 1 minus x plus c. Yeah, again, this is on the simpler end. It's just a little weird looking because it's kind of new. As Liana said, if we took the 4 out from the beginning, it would actually be a lot easier to just do in your head, I think. But this is just to remind you guys of how u substitution is going to work. So you guys take a look at 3 and 4. Take a couple minutes to do that. All right, let's check. So, number 3 is an example where hopefully, as you're doing more practice with this, you could see that if we integrate this, it's just e to the x squared plus c. Like 2x is the derivative of x squared, so it's sitting right there. If we took the derivative of e to the x squared, we would get 2x e to the x squared. So that's what you want to be on the lookout for. Something like number 4 is a little bit complicated, but hopefully we're noticing like 1 over 2x squared does look a lot like the derivative of 1 over x. So that's our indicator that we actually can do this problem. But for number 3, again, it's still new. What would I want to make u if I was doing u substitution? For number 3. Yeah. What would u equal? X squared. What's the derivative of x squared? 2x. Okay, we have 2x dx right there, so we don't need to manipulate anything. We can just make this the integral of e to the u, and we integrate that as just e to the u plus c, and so we get that right there. So in number 4, okay. U is going to be 1 over x. The derivative of 1 over x is what's the derivative of 1 over x?
1 over negative x.
Yeah. So we almost have that. Now, just to let you know, like if for some reason we had something like 2x cubed on the bottom, if this is our du and we have 2x cubed, that is not a multiple of the derivative. That is a different function. We're not allowed to just multiply by x. That changes the function. This would be impossible to integrate. Anything other than something x squared on the bottom of this function would be impossible to integrate. Even if it was like 2x plus 1 on the bottom of this, impossible to integrate, because it's not, I can't just multiply this by some number, a constant, and have it match, okay? So this is just a good reminder that not all problems are possible to integrate. Or not all problems fall neatly into U substitution. In Calc 2, you learn a lot of other integration techniques that could help you with stuff like this potentially. Maybe not this, I'm not even sure. But some integrals are actually just impossible to take by hand. So it's kind of interesting. We need this to be a multiple of the derivative. Like I can take a number and multiply it and get that right there. So what number am I multiplying both sides by to get it to match? 1/2? Negative 1/2, yes. I need to multiply both sides by negative 1/2. So I have negative 1/2 du equals now 1 over 2x squared dx. Now it matches. And so now I have negative 1/2 integral of e to the u du. And so remember, our negative 1/2 du is replacing all of this. And what this allows us to do is now just integrate. So it'd be negative 1/2 e to the u plus c, negative 1/2 e to the 1 over x plus c. Okay. Questions? Okay. I want to look at here at number 6, and then we're going to move on to natural logs. Turn to your neighbor. What would we do to approach this problem right here? What ideas do you have?
Should there be? I mean, so e to the 3x 2
Okay, how do we want to go about starting this problem right here? What's our strategy? For sure, what were we saying over there? Yes, that's exactly what we want to do. Yep. So we can just divide e to the x to each of these. So the problem right now is we can't really choose something that's u. Like the derivative of this is definitely not that. And we have a whole like addition problem up here. So yeah, this is one of our integration techniques. If it's helpful to think about it, you can break it down into these separate steps, like splitting the fraction. But really all we're doing is just dividing that to each of those terms. Does anyone remember what that property is called when we divide something to a whole addition problem? That is the distributive property, right? Right? It doesn't look like it. Isn't this the same as 1 over e to the x times e to the 4x plus 2 e to the x plus 1? So isn't that what I'm doing right there? Yeah, that's a distributive property. So we can distribute division just like we can distribute multiplication. Okay, so this means we have the integral of e to the what? 3x plus 2 plus, 1 over e to the x. I would just go ahead and change that to e to the negative x. Technically, all this should be in parentheses because it's an addition problem, but if you have that dx on the end, it's fine. Now that it's just an addition problem, we can integrate each of these things separately. So just reminding you guys of the rules. This is the same thing as the integral of e to the 3x plus the integral of 2 plus the integral of e to the negative x. You cannot do that with the original problem because that's a division problem. But addition or subtraction, you can split up into separate integrals. Okay, so this would be 1/3 e to the 3x plus 2x minus e to the negative x plus c. You don't have to write that middle part, obviously, but just a reminder of how integrals work. Okay, any questions? All right, let's go to 2 pages later, integrals of natural log. Okay, you don't need to write this because you already have it written in the packet, but if it's helpful, go ahead. So if we take the derivative of natural log of x, it's just 1 over x. If we take the derivative of some function f of x, what we get is the derivative over f of x. So there's nothing fancy here. What we're integrating is just the opposite of this. So if we integrate 1 over x, we get natural log of x plus c. If we integrate something like that, it's just natural log of f of x plus c. So what we're looking for to integrate something that's going to be natural log is a function that's to the negative first power with its derivative, let's say, multiplied. And so one of our challenges here with natural log, I'm trying to look ahead and see if there's good examples. Yes. One of our challenges here with natural log is that it tends to look like some other functions. And so what is going to be really important is that we can, no pun intended, differentiate between the different things that we're trying to integrate. So let's look at some examples and it'll make more sense. So, now some easy ones here. If we're just integrating 4 over x, we can just take that 4 out. We're just integrating 1 over x, and so this is just for natural log of x. If we're integrating something like 1 over 5x minus 2, so again, what we want to notice is 5x minus 2 is to the negative first power. That's really important. What's the derivative of 5x minus 2? 5. So u is going to be 5x minus 2. It's there on the bottom. It's to the negative first power. The derivative of that would be 5. Okay, we look and say, we don't have a 5 dx, we have a 1 dx. So we need to multiply both sides by 1/5 or divide both sides by 5. Bless you. And so what this allows us to do is rewrite our original problem there as 1/5 1/u du. So when we're integrating 1/u, again, it's 1/u, not 1/u squared or u cubed or 1/√u. It's to the negative first power. That's what's different. Now we can integrate this and make it 1/5 natural log of u plus c. I mentioned this last time. Sometimes you'll see in a multiple choice question, like the answer is like written like that with absolute value brackets. That's fine too. It's the same. Like you can treat it as the same thing. It's basically just a reminder that the inside of a log has to always be positive. So while x might have a lot of different numbers in its domain, like when you use it in a natural log, we always have to keep the inside positive. So usually just write it with parentheses, but if you ever see it with brackets, just treat it like it's the same. Yeah. You guys do number 3. Do number 3 and 4, actually. All right, let's check these. So, in number 1, if I don't do anything to the function before I start, what would u equal? What's u going to be? Okay, 3 minus 6x. Notice that's on the bottom to the first power, so I'm already thinking natural log. Also, we're learning about natural log, so I'm already thinking natural log. What's the derivative of that? Negative 6. Okay, we have 4 instead. So sometimes, you know, the math gets a little bit weird here, but like all we need to do is multiply this by negative 4/6 on both sides. That will cancel out the negative 6 and give us a positive 4 instead. So that's negative 2/3 du equals 4 dx. So it's not the worst thing in the world. Something that we can do to make life a little bit easier with this problem here is from the very beginning we could factor out a 4/3 so that we just have 1 over 1 minus 2x dx. It's just a little bit easier to work with, and you kind of just leave that 4/3 on the outside. But it's just an option you have. So when I do this here, we have negative 2/3 on the outside, and we have 1 over u on the inside. And so this is just negative 2/3 natural log of u plus c. Same thing in number 4, like I can take the 7 out from the very beginning. And just think about it like that. So I'm going to make u x squared minus 4. Derivative of that would be 2x. So I see I just have a 1x, not a 2x, so I'm going to multiply both sides by 1/2. So when I substitute everything back in, it becomes 7/2 integral of 1 over u du. Again, this whole thing, x squared minus 4, is to the first power. And 7x is a multiple of its derivative. So this just becomes 7/2 natural log of x squared minus 4. So once you get the hang of this and you start noticing it, it's not that bad. It's the same as integrating everything else. Here's where it starts to get a little trickier. So as I look at number 5, first of all, what I want you guys to notice right away is this is square rooted right there. So if we're integrating this, is it going to be natural log? It's not going to be natural log. For it to be natural log, our bottom has to be to the first power. So if there's a square root, already I'm thinking this is not natural log, and that's what we want to notice right away. So as we do this, now if you don't notice it right away, I'll tell you when you need to notice it, otherwise you'll get it wrong. So if we make our u the inside function, du is negative 2x dx. Multiply both sides by negative 1/2 so that we get x dx. And so then we substitute, which would be negative 1/2 integral of 1 over root u. Or I could write that as negative 1/2 u to the negative 1/2. If you didn't recognize it in the beginning, you got to recognize it here. This is when we integrate that, it's not natural log. What rule am I using to integrate this? Yeah, this is just reverse power rule. So anything and everything, well, yeah, for now, that's not to the negative first power. Like we have to use reverse power rule. So that means we increase the power by 1, so we have negative 1/2 u to the 1/2, divide by the new power, so that means times 2 plus c. So we just get negative u to the 1/2 plus c, or negative root 16 minus x squared plus c. Because what's going to happen is everything's going to be mixed together, and you're going to have to be able to tell what's reverse power rule and what is natural log, and just for fun, what's inverse trig, because we're going to learn that next week. Yes, next Tuesday. Because inverse trig also looks a lot like this. So, in number 6, is number 6 going to be a natural log integral, or is it going to be reverse power rule? Reverse power rule, yeah, we can see the 1/3 power right there. Okay. Number 7, okay, I see x to the negative first power on the bottom there. So maybe I'm thinking this is going to be natural log. But do we see the derivative of x on top here? No, we do not. Okay. In this one here, what should u equal? Yeah, natural log of x. So I see my outside function here. This is inside, so that's going to be u. And what's the derivative of natural log? Okay, so we have the derivative. So what I'm integrating here is actually u to the 4th. And what's the integral of u to the 4th? Yep. Okay, I want you guys to talk about number 9 and number 11 with your partner. How are you going to do that? What's u going to equal? Is this natural log? What do we do? Talk about it.
You think use what? Tangent x or just normal? I think so. Tangent x. Makes sense.
Oh, 11 is easy.
Okay, let's check these. So, if we remember, we can't just integrate tangent. That's not part of our trig integrals. So what do we need to do with tangent in order to be able to integrate it? How'd you guys rewrite it? Sine over cosine. Okay. So tangent is sine over cosine. Which one of these do we want to pick for u? Cosine, yeah. So what I want you guys to notice, what we want to be able to notice is we have something to the negative, something to the negative first power. Cosine is to the negative first power. Its derivative, or a multiple of the derivative, is on top. This is what natural log integrals look like. Now, the derivative of cosine is positive sign or negative sign? Negative sign. Okay, so we need a negative du to make that positive. But that allows us to do our u substitution here to make it negative 1 over u. So when we integrate this, it's negative natural log of u or negative natural log of cosine. Oops. So that's the integral of tangent. In number 11, I see something to the first power, the negative first power. What would be the derivative of the bottom? What would it be? Cosine, yeah, just cosine. So the derivative's right there on top. We should not need to use u substitution because the exact derivative is on top. We don't have to manipulate it at all. This is just natural log of 2 plus sine x. If you do use substitution, it's just u and du, and then it's 1 over u. Okay, we're going to look at one more example question so far. We're going to go to number 25. Take 1 minute to talk about this with your neighbor. How do we do this?
You can't separate this, right? It's like different signs.
Jamie, what'd you make u?
I made you e to the x plus e to the negative x.
Okay, so this bottom part there. What's the derivative of that?
The derivative of that would be e to the x minus e to the negative x.
Okay. Do we have that derivative? Yeah. Okay, so that's du. Oh, so we're just integrating 1 over u du. So it's just natural log of u plus c. So it's crazy looking, but it's actually quite simple if you see it. You see something to the negative first power. You see its derivative on top. That's natural log. We'll do some more practice with this next class. But you guys will have a delta math to do. And yeah, that's it.